Hello, I am Dr. Jason Mast, and this is the lecture covering Chapter 4. In this lecture, I will go over heat, temperature, the states of matter, thermal expansion, the ideal gas law, the zeroth, first, and second laws of thermodynamics, as well as machines such as engines and refrigerators.
Bulk matter is composed of a huge number of molecules or atoms. For example, 1 pound of water is composed of 1.5 times 10 to the power of 25 H2O molecules. It is impossible to track the motion of each of these molecules, and even if we could, there would be far too much information to process. And so, instead, we have macroscopic parameters to describe the ensemble of atoms and molecules. Temperature is one of those parameters. It is a measure of the total internal energy of a collection of atoms and molecules. More energetic particles have a higher temperature, and so the temperature is a measure of hotness. Thermal energy, also known as internal energy, is the total microscopic kinetic and potential energies of matter.
Next, let's look at the temperature scales that you are likely to encounter. Each of these scales have a long history and have gradually changed over time. First is the Celsius scale, which is common outside the United States. It defines two reference points, the freezing point of water and the boiling point of water. These are defined to be 0 and 100 degrees Celsius respectively. Second is the Fahrenheit scale, which is used in the United States. Originally, it defined 0 degrees Fahrenheit to be the freezing point of brine, which is a solution of salt water, and 100 degrees Fahrenheit to be the average human body temperature. The scale has been modified over time and currently uses 32 and 212 degrees Fahrenheit as a freezing and boiling point of water respectively. With these 4 points, a temperature conversion can be derived as shown here. Finally is the Kelvin scale, which is the official SI unit of temperature. The Kelvin scale is simply the Celsius scale shifted so that absolute zero is 0 Kelvin. Absolute zero temperature is the temperature in which all atoms have no kinetic or potential energy. It is impossible to reach this temperature, but research teams have been able to get extremely close to it. Because the Kelvin scale is just a shifted Celsius scale, a change in temperature on the Celsius scale will have the same value as on the Kelvin scale. For example, if an object increases its temperature by 5 degrees Celsius, then you could instead say that it increases its temperature by 5 Kelvin. Alternatively, on the Fahrenheit scale, you'd have to say that it increased by 9 degrees Fahrenheit. The other point on the Kelvin scale is the temperature of the triple point of water, which is marginally higher than the freezing point of water at 1 atmosphere. This temperature is 273.16 Kelvin. Imagine we have two systems, A and B, such that the temperature of A is greater than the temperature of B. If we bring these two systems into thermal contact, heat will flow from the hot system into the cold system until the two systems have the same temperature. This is called thermal equilibrium. If a third system, C, is brought into contact and comes to equilibrium with system B, then it is the case that systems A and C are also in thermal equilibrium. This is known as the zeroth law of thermodynamics, and it is a statement of transitivity of temperature. That is to say that if the temperature of system A and B are equal, and the temperatures of systems B and C are equal, then therefore the temperatures of systems A and C are also equal. This law allows for the existence of thermometers, which are instruments that measure temperature. Most materials will expand as they are heated and contract when they are cooled. The relative change in length is proportional to the change in temperature. The coefficient of proportionality alpha is called the coefficient of thermal expansion, and for steel is on the order of 12 parts per million per Kelvin. Here is a rod with an initial length L sub 0, and after it is heated it has increased by an amount delta L. One application of this is the heating of nuts and bolts to release them when they are rusted, as heating them causes them to expand and can potentially free them. Another interesting fact is that water has a negative coefficient of thermal expansion for temperatures below about 4 degrees Celsius, and this fact is important for the development of life on Earth.
Let's look at solids and liquids. Solids are a rigid collection of atoms, and because of that, solids have a definite shape and volume. The bonds between atoms in a solid can be modeled as springs, where the nucleus of each atom can only vibrate around a fixed center point. Solids can generally be broken into two categories. First are crystalline solids. A crystal is built from repeating units. Examples of crystals are metals, minerals, and most ceramics. The next type of solid are the amorphous solids, in which the molecules do not form repeating units. An example of an amorphous solid is glass. Liquids are formed when the bonds between molecules is weak, and the molecules are allowed to vibrate, rotate, tumble, and diffuse slowly. Because of this, liquids occupy a definite volume, but their shape is indefinite. Next, let's look at gases and plasmas. Gases are a collection of atoms and molecules that have no structure or force holding them together. In an ideal gas, the atoms and molecules never interact. There are only elastic collisions with the container. And contrary to popular belief, if two ideal gas atoms cross each other's path, they do not collide. Instead, they pass right through each other. The atoms and molecules of a gas move very quickly, on average 350 meters per second. They are also free to rotate and vibrate. Because of these properties, an uncontained gas has no definite shape or volume. Plasmas can be thought of as very hot pressurized gas of ions. Ions are charged particles such as electrons or atoms with an unequal number of protons and electrons. The dynamics of plasmas are dominated by the electromagnetic force. Examples of plasmas are hot fires, lightning, solar winds, and stars.
Let's now look at the atomic source of pressure. In this cartoon, an atom of gas collides elastically with a wall. Here's the atom just before the collision, and here it is again just after the collision. In this animation, we will graphically find the atom's change in velocity. The atom's velocity changed directions. Therefore, there was a change in momentum equal to the atom's mass multiplied by its change in velocity. A change in the atom's momentum means the wall applied a force to cause that change. This is from the impulse momentum theorem. There are a huge number of gas atoms colliding with the wall. All are exerting a force on the wall. Pressure is defined as the ratio between the total force applied to the wall and the surface area of the wall. P equals F divided by A. Let's now look at the relationship between the temperature and the pressure of an ideal gas. We know that temperature determines the thermal energy of a system, and that thermal energy is just the total kinetic energy for an ideal gas. Kinetic energy is determined by the atom's speed, and the speed of a gas atom determines the impulse with the wall. And from the impulse momentum theorem, we know that the impulse is proportional to the force. And pressure is defined as a relationship between the force and the surface area. We can combine all these pieces of logic together to come to the conclusion that the pressure must be proportional to the temperature, and this is known as Gay-Lussac's law. We saw earlier that we can find the amount of impulse by looking at how the velocity changes. If the temperature of the gas increases, the velocity is higher, and so therefore the impulse is higher. So we come to the conclusion that the pressure increases as the temperature increases. Let's now find the relationship that the number of atoms in the gas have to the volume and the pressure. We know that the impulse each gas atom has with the wall determines the force it has with the wall. And so the total force acted on the wall must be proportional to the total number of atoms that are in the gas. The pressure of a gas will be proportional to the exerted force, and so we can combine those two statements to come to the conclusion that the pressure will be proportional to the number of atoms in the gas. Mass density is calculated by taking the mass of a gas and dividing it by the volume that that gas occupies. The mass of a gas will be proportional to the number of atoms in the gas. And so we can combine those two statements to come to the conclusion that the density of a gas will be proportional to its number density. That is the number of atoms in the gas divided by the volume that it occupies. And then from this we can get Avogadro's law, which is that if the pressure and the temperature of the gas are held constant, the volume will be proportional to the number of atoms in the gas. So if the number of atoms in the gas double while the pressure and the temperature are held constant, the volume must also double. Now look at the relationship between the volume and pressure of an ideal gas. We know that the pressure of a gas is determined by the collisions between the gas molecules and the container's wall, and so the pressure will be proportional to the number of collisions with the wall. The number of collisions that the wall experiences will depend on the amount of time it takes the molecule of gas to reach the wall. Longer times will mean there are fewer collisions, and so the number of collisions is inversely proportional to the time of flight. The time it takes a molecule of gas to reach the wall will depend on the traveled distance. Longer distances take longer time for a given speed. And the travel distance will depend on how big the container is, so the distance is proportional to the volume. Combining these four pieces of logic together, we come to Boyle's law, which says that so long as the amount of gas and the gas's temperature are constant, the pressure will be inversely proportional to the volume. Let's look at the relationship between the volume and temperature of an ideal gas. Two gases, A and B, are separated by an ideal movable partition. An ideal movable partition is massless, doesn't allow heat transfer, and moves freely without friction. Initially, the two gases have the same temperature and pressure. When a heat source is in thermal contact with gas A, its temperature will increase, and we know from Gay-Lussac's law that its pressure will also increase. Because the partition is free to move without friction, it will move to the right, compressing gas B. As the partition moves, the temperature does not change. However, the pressure of gas A will decrease and its volume will increase. We expect that from Boyle's law. But we can also see that the volume increased because the temperature increased, and this is Charles' law. Let's now use what we have learned so far to derive the ideal gas law. First, from Gay-Lussac's law, we saw that the pressure of a gas was proportional to its temperature. A higher temperature meant a higher pressure. Then we saw that because the number of atoms in a gas determined the number of collisions with the wall, that the pressure of a gas was proportional to the number of gas atoms. Then we saw from Boyle's law that the pressure of a gas was going to be inversely proportional to its volume, so a larger volume of gas held at constant temperature would have a smaller pressure. And we saw Avogadro's law, which said that the number of gas atoms in a given container was proportional to its volume. And finally, we saw Charles' law, which said that the volume of a gas was going to be proportional to its temperature. We can combine all of these statements to get to the ideal gas law, which can be written as PV equals K sub B in T, or, which is common in chemistry, PV equals nRT. where K sub B is Boltzmann's constant, and it converts Kelvin into joules. Lowercase n is the amount of gas as measured in moles, and it's taken as the ratio between the number of atoms divided by Avogadro's number. Avogadro's number is the number of molecules that make up 1 mole of that substance. And R is the ideal gas constant.
Let's do an example problem of finding the volume of an ideal gas. How much space, in liters, does 1 mole of an ideal gas at 300 Kelvin and 1 atmosphere of pressure occupy? First, I'll identify the pressure, which is 1 atmosphere. 1 atmosphere is the pressure from the atmosphere sitting on top of you, and it is equal to 101,325 pascals, where a pascal is the standard SI unit of pressure, and it is defined as 1 Newton per square meter. First, we'll start by writing down the ideal gas law and solving for the volume. PV equals nRT, and so therefore the volume, V, equals nRT multiplied by the inverse of the pressure. Here I have highlighted N, the number of moles in green, the ideal gas constant in blue, the absolute temperature in red, and the pressure in purple. Then we'll go ahead and plug in all of the values. We'll get this expression. You should notice that I keep all of the units in my work. This will help me keep track of everything. The first factor is N, the number of moles, which is 1 mole. The second factor is the ideal gas constant, and it is in blue. The third factor is the absolute temperature. The fourth factor is the reciprocal of the pressure, which I've just plugged in the value in pascals. The factor after that converts pascals into newtons per square meter. And then the final factor converts joules into Newton meters, which is needed to convert the joules and the ideal gas constant into Newton meters. When you do this, you can see that all of the units cancel except for cubic meters in the end, which makes sense because this is a measurement of volume. When all of the multiplication and division is done, we get that the volume is 0.025 square meters. The final step is to convert this into liters. First, we must recognize that 1 cubic centimeter is equal to 1 milliliter. And then 1 meter is defined as 100 centimeters. We can take that equation and cubic. And so 1 cubic meter is 100 centimeters cubed. And when that is done, we get that 1 cubic meter is a million cubic centimeters. A million is 1,000 times 1,000, and a cubic centimeter is a milliliter. 1,000 milliliters is a liter, and so we get that 1 cubic meter is equal to 1,000 liters. We can then use that to convert the volume, and we get that the volume of 1 mole of an ideal gas at 300 Kelvin and 1 atmosphere of pressure is 25 liters.
If a hot object is placed into a cold environment, heat, which is the transfer of thermal energy, will flow out of the hot object and into the cold environment. Over time, heat will flow out of the object, cooling it, and into the environment, warming it. As these two get closer together, the amount of heat transfer will decrease. The object will cool and the environment will warm until they reach the same temperature. This is thermal equilibrium. Let's now look at the various types of heat transfer. Conduction is the transfer of heat from contact with a hot surface. The rate of heat flux is proportional to the temperature gradient. A quantity of flux is the quantity per unit surface area, and rate is per unit time. So Q divided by A divided by delta T is the rate of heat flux. A gradient is the change in quantity per unit distance. So the temperature gradient is the change in temperature per length. The proportionality constant, K, is the thermal conductivity. Very good thermal conductors have large K values. In this image, heat flows from the very hot red left-hand side to the cold right-hand side, which is a distance L away. Convection is heat transfer through the flow of the surrounding fluids. A warm body of air has a lower density than a cooler body of air. Because of that, a buoyant force allows for it to rise. As the hot gas molecules rise, they give up their kinetic energy to gain potential energy due to gravity, and slow down. The hot air below then pushes that air out of the way, and sometimes can form vortices. Evaporation is the removal of heat by mechanically removing hot particles. This can happen when hot particles of a fluid rise to the surface and are able to escape into the atmosphere above. Let's now look at thermal radiation. All warm bodies emit thermal radiation. The amount and wavelength of that radiation depends on the absolute temperature of the object. The peak wavelength is the wavelength of radiation that is most common. Visible light has wavelengths that are 400 to 800 nanometers, and that is the kind of radiation that our eyes can detect. For warm bodies at 330 Kelvin, the peak wavelength is 8 to 9,000 nanometers, which is well outside the range of our eyes, and that's why we cannot detect them. Sigma in this equation is the Stefan-Boltzmann constant, and E is the emissivity, which is a parameter that varies from 0 to 1 and determines how good of a radiator the object is. This is an image taken from a thermal camera of a cat sitting in front of a window and eating out of a dish. It shows that his eyes are very warm when compared to the rest of his body. It also shows that as he eats from the dish, some of his radiation warms the dish. The image also shows that the window behind him, the table beneath him, will reflect thermal radiation. An object that is in thermal equilibrium with its surroundings will absorb the same amount of radiation that it is emitted. Heat can be added or subtracted from matter to change its temperature. Solids and liquids are, for the most part, incompressible, and so the amount of heat transfer is proportional to the change in the object's temperature. The proportionality constant is the heat capacity, which is the object's mass multiplied by the specific heat capacity. Specific heat capacity is a property of matter that also depends on its phase. For gases, the idea is the same, except that the heat needed for a given temperature change depends on whether the gas is at constant pressure or if it is contained and at a constant volume. To change the intermolecular forces that determine the phase of matter, a significant amount of heat is needed and is simply proportional to the object's mass. The proportionality constant, L, is the latent heat, and there are different latent heats for different phase changes. For example, the latent heat of melting or fusion is for the solid-liquid transition, and the latent heat of vaporization is used to vaporize a liquid. One important thing to remember is that phase change always occur at constant pressure and constant temperature. So once the object's temperature is brought to the temperature of the phase change, all extra heat goes into changing its phase and not its temperature. Let's do an example of heating half a kilogram of water at 1 atmosphere. In this example problem, we will add heat to half a kilogram of water, and we'll record the amount of heat added in this ledger, and then we'll observe how the temperature changes. Let's go ahead and record the values that we need. First, we'll start with ice at negative 20 degrees Celsius, and then we'll warm it to its melting point at 0 degrees Celsius. That water will then be warmed until it vaporizes at 100 degrees Celsius, and then that water vapor will be heated an additional 10 degrees Celsius. Here are the specific heat capacities of solid ice, liquid water, and water vapor at constant pressure. And then here are the latent heats of fusion and vaporization in kilojoules per kilogram. So we'll start with warming ice at negative 20 degrees Celsius up to 0 degrees Celsius. So we multiply the mass of the ice, multiplied by the specific heat of solid ice, multiplied by the temperature difference. The temperature difference here is just the final temperature, which is the melting point, minus the initial temperature, which is negative 20 degrees Celsius. At this point, the ice can be melted. So we use the latent heat of melting, which is just the mass of the ice multiplied by the latent heat, and we get 667 kilojoules. You should notice that this is approximately 8 times the heat needed to warm the ice. It takes a lot of heat to cause a phase transition. Now that the ice has melted, that water can be warmed. And so the heat needed to do this is similar to before. It's the mass of the water multiplied by the heat capacity of the water multiplied by the temperature difference. This time the temperature difference is from the melting point at 0 degrees Celsius up to the vaporization point at 100 degrees Celsius. Now that the water is at the boiling point, heat can be added to vaporize the water. And the amount of heat needed to do this is very significant. And it's so much that I cannot draw it to scale in this graph. But it ends up being more than 1100 kilojoules. Once the water has vaporized, we can then continue to heat the water. If we choose to heat the water at constant pressure, to find the amount of heat needed, it's just the mass of the water vapor multiplied by the heat capacity of the water vapor at constant pressure multiplied by the change in temperature, which in this case is 10 degrees Celsius. Then we can add up all those heats to find that the total heat needed to bring ice at negative 20 degrees Celsius up to water vapor at 110 degrees Celsius is more than 1500 kilojoules. Global warming is one aspect of climate change where radiation from the sun warms the earth. Carbon dioxide and other greenhouse gases accumulate in the atmosphere from the burning of hydrocarbon fuels for energy. These gases prevent radiation from leaving the earth, thereby increasing the earth's thermal energy. The biggest problem with global warming is that it drives many positive feedback loops. For example, sea ice reflects radiation from the sun, and when it melts, more heat is absorbed by the Earth's oceans, which in turn melt more sea ice. Additionally, because it is warmer, more water vapor accumulates in the atmosphere, and water vapor is a stronger greenhouse gas than carbon dioxide. Because of this, the problem of global warming should be dealt with sooner rather than later. As we saw in the previous lecture, if the system does work on the environment, the system's energy will decrease. And if the environment does work on the system's energy will increase. We combine that to come up with the energy law, which says that the total change in energy of a system is equal to the net work done. We've also seen that there can be a transfer of energy through heat, and if the system is heated from the environment, then the system's energy will increase. And if the system cools by heat leaving, then the system's energy will decrease. We can add that to our energy law to come up with the first law of thermodynamics, which says that the total change in energy of a system is equal to the total work plus the total heat, where the total change in energy of a system is equal to the change in kinetic energy plus the change in potential energy plus the change in thermal energy. The change in kinetic and change in potential energy is sometimes referred to as the change in mechanical energy of a system. This first law of thermodynamics makes two important claims. It claims that not only work but also heat are methods of transferring energy into or out of a system. And it also claims that the energy of a system is conserved if the total work plus the total heat add up to 0. For the next topic, we'll look at machines. I'll draw machines as a yellow circle with the capital letter M in the middle. Machines are devices that take in energy through heat or work and output energy through heat or work. They also operate in a cycle, that is to say that their initial state is equal to their final state. These machines have a gas inside of them, and the state of a gas is determined by its pressure, volume, and temperature. If the initial and final states are equal, that means the initial and final pressures are equal, the initial and final volumes are equal, the initial and final temperatures are equal. Energy is a function of state. If the state doesn't change over the course of a cycle, that means that there is no change in energy over the course of a cycle. The first machine we'll look at is called a heat engine. An example of one of these is the internal combustion engine of a car. The purpose of these devices is to pull in heat from a hot reservoir. For example, the burning of fossil fuels generates a lot of heat that can do work. And the work is the purpose for building these machines. However, no heat engine is perfect. Some of this energy gets wasted, and this is heat that is dumped into a cold reservoir. The heat pulled from a hot reservoir is called Q sub H, and the heat dumped into a cold reservoir called Q sub C. Because there is no change in energy over the course of a cycle, the input energies must be equal to the output energies. In the case of a heat engine, the input energy is heat pulled from a hot reservoir, Q sub H. The output energies are the work done and the heat dumped into the cold reservoir, Q sub C. The heat dumped into a cold reservoir is the heat that is exhaust through the tailpipe at the back of the vehicle. We would like some sort of metric to be able to compare different heat engines, and one metric is called the efficiency, and it varies from 0 to 100%. These metrics are calculated by looking at the energy that we want and dividing by the energy that we have to pay for. In the case of a heat engine, the energy that we want is the work. That's the whole purpose of building these devices. Then the energy that we have to pay for is the heat transfer from the hot reservoir, Q sub H. We have to pay for the fossil fuels that can be burned that will drive the machine to do the work. The next machine is called a heat pump, or more commonly referred to as a refrigerator. The purpose of these devices is to pull heat out of a cold reservoir. A cold reservoir could be a bedroom, an office space, or the cabin of a refrigerator that stores food. This device will then pull that heat out of the cold reservoir and then dump it into a hot reservoir. In the case of a refrigerator that stores food, a hot reservoir is the kitchen. Now, heat naturally will not flow in this direction, but we can build a machine that will force this to happen so long as there is an input of work. Just like before, the total input energies must be equal to the total output energies. In the case of a heat pump, the input energies are the work and the heat pulled from the cold reservoir. The output energies are the heat that is dumped into the hot reservoir. And just like before, we need some sort of metric to be able to judge how good this device is. And for heat pumps, this is called the coefficient of performance. And just like before, we want to take the ratio of the energy transfer that is desired and divide by the energy transfer that we have to pay for. In the case of a heat engine, we desire work and we pay for heat from the hot reservoir. In the case of a heat pump, we desire heat being pulled out of the cold reservoir, but we have to pay for the work. In the case of most refrigerators, you pay for it in the form of an electric bill. So the coefficient of performance is the heat transfer from the cold reservoir divided by the work. Using what you have learned so far, describe these four machines. Are they realistic machines? Are they ideal? If they are realistic, describe what they do. And if the machine is real, develop a metric of goodness to describe it. Note that the machine in D is really a composite of two machines, M1 and M2, connected through a transfer of work. For the answers, see the appendix.
Let's do another example problem of computing machine work. A machine can do work with a 40% efficiency. If the machine is supplied with 320 kilocalories of energy, how much work in kilojoules can the machine do? If the machine operates in a cycle and each cycle performs 15 kilojoules of work, how many cycles can be done with the original 320 kilocalories? We'll start with the definition of efficiency. Efficiency is the output divided by the input. In this machine, the output is work and it is supplied with an input of energy. Efficiency is 40%, which is 0.40, and the input energy is 320 kilocalories. So we can come up with this expression. All we need to do now is solve for the work. The work, W, is equal to 128 kilocalories. Now we need to convert this to kilojoules. To do this, you have to know that 1 kilocalorie is equal to 4.184 kilojoules. After the unit conversion, we get that the work done is 535.552 kilojoules. If you look at the original problem statement, all of the numbers involved only have two significant figures, and so there can only be two significant figures in this result. And that is that the work done is 540 kilojoules. Now we need to solve for the number of cycles that can be done. If each cycle does 15 kilojoules of energy, then we need to find the number multiplied by that 15 kilojoules that will be equal to the total amount of work, which is 540 kilojoules. Plugging in the values, and in the end, we get that the number of cycles is approximately 36 cycles.
Let's review the refrigeration cycle. First, a gas called a refrigerant enters a mechanical device called a compressor. This device takes in electrical work to compress the gas. As the gas is compressed, it becomes very hot. To remove thermal energy of the refrigerant, it is passed through a heat exchanger called a condenser that is commonly found outside of buildings or in the front of a vehicle next to the radiator. The refrigerant will lose energy and may enter the liquid state. The refrigerant is then allowed to expand through a device called an orifice tube. As the refrigerant expands, it passes through another heat exchanger that is inside a building or in the cabin of a vehicle, and that expanding gas pulls heat from the surrounding air, thereby cooling it, after which the refrigerant is returned to the compressor for an additional cycle. Before we get into the second law, I want to warn you that there are a lot of misinformation on the internet about what the second law is or implications of it, so please be very careful. There are several different ways of expressing the second law of thermodynamics. At a fundamental level, the second law says that the entropy of an isolated system cannot decrease. Entropy is a measure of the number of states available to a system. For example, if a collection of atoms form a crystal, there are only a few ways in which the atoms can be organized to form that crystal, and so the entropy is very low. But for the same atoms in a gas phase, there are many ways in which those atoms can be organized to form that gas, and so the entropy is very high. For the purposes of this class, the second law says that ideal machines cannot exist. In the case of heat engines, no heat engine can exist that will convert heat solely into work, or in other words, no heat engine can be 100% efficient. In the case of heat pumps, no refrigerator can pump heat from a cold reservoir into a hot reservoir without an input of work. Let's go ahead and review today's key lessons. First, we looked at temperature and thermal energy. Thermal energy is the total microscopic energy of the atoms and molecules that make up bulk matter, and temperature is a gauge for thermal energy. The 0th law of thermodynamics says that if systems A and B are in thermal equilibrium, and that systems B and C are in thermal equilibrium, then it is the case that systems A and C are also in thermal equilibrium. This law allows for the existence of thermometers, which are instruments to measure temperature. We also saw that the length of solid objects can change depending on the change in temperature. Then we looked at states of matter and derived the ideal gas law. Solids are a rigid collection of atoms in which the atoms only interact with their neighbors and are allowed to vibrate around a center point. The atoms in a liquid interact weakly with each other, but they are allowed to rotate, tumble, and slowly diffuse. The atoms of gases rarely interact, and in an ideal gas, they never interact, and so the particles of a gas are free to move around very quickly. A plasma is a hot pressurized gas of ions. We then saw that elastic collisions of the atoms in a gas with the container's wall is the source of pressure, and from that we derive the ideal gas law, PV equals NKT. We then saw that heat is the transfer of thermal energy into or out of a system. Heat going into a system is called heating, and heat leaving a system is called cooling. There are 4 common modes of heat transfer. Conduction, which is heat transfer through contact. Convection, which is heat transfer through a surrounding fluid. Evaporation, where hot atoms are removed. And thermal radiation, where warm objects emit infrared light. We also saw that heat transfer into or out of a mass can change its temperature, and we saw that a significant heat transfer is needed to change the phase of matter. We then modify the energy equation to include heat transfer to get the first law of thermodynamics, which says that the change in internal energy of a system is equal to the net heat transfer plus the net work done. Finally, we looked at machines. We saw that they operate in a cycle, and so the net input energy and output energy must be equal. We analyzed heat engines, which take in heat from a hot reservoir to do work, and heat pumps, which force heat to flow into a hot reservoir with an input of work. Finally, we saw that the second law of thermodynamics forbids the existence of ideal machines. Let's review the 4 machines. In machine A, heat is transferred from a hot reservoir into a cold reservoir, and none of the energy is used to produce work. This is not a machine at all. It simply represents thermal conduction. In machine B, work is done from an equal amount of heat pulled from a hot reservoir. This represents an ideal heat engine with 100% efficiency and violates the second law of thermodynamics, and so is not a real machine. In machine C, an input of work is transformed into an output of work, with a small amount of heat wasted by being dumped into a cold reservoir. This is a real machine, and an example would be an electric engine, also known as an electric motor, which is a device that converts electrical work into mechanical work that can then rotate a shaft. The metric of goodness would be defined as the ratio between the output and input work. Machine D is a composite machine composed of a heat engine M1 that drives a heat pump M2. An example could be a backup diesel engine that powers a refrigerator. Note, the reservoir that heat is dumped into by M2, the refrigerator, could be the same reservoir that M1, the heat engine, dumps heat into. The metric of goodness would be the ratio between the heat pulled from the heat pump and the heat used to operate the engine.